Yeah, we're happy to start off the lighting session today. I'm Eva Pribila, product manager at MBJ Imaging, and joining me today is my colleague, Ivan Kempf.
Greetings.
He's our application engineer. And before we start off, I would like to shortly introduce MBJ Imaging. We are specialized in LED lighting for machine vision. We've been here now for 10 years. We are celebrating our 10 years anniversary this year. And at the beginning, there were two engineers that had the strong belief that industrial high-quality lighting should and could be available at fair pricing. And that's what we are specialized now in today. We're quite proud that everything we do takes place in Ahrensburg, which is just a few kilometers from Hamburg in the north of Germany. We do our development there, our production, the whole sales marketing team is there. So we have short ways, we work closely together, and we are quite flexible in what we do. We are not just a lighting manufacturer, we are a team of specialists. We have our own engineers here at our facility. We have engineers for electronics, for mechanics, for software. So we are capable of realizing customer-specific projects, of developing whole lighting solutions, and we do that at fair prices. So that's still our main goal that we strive to achieve. And we also offer some standard products that you can see also at our booth over there. And for the standard product line, we focus on adaptability, modularity, so you can accommodate various lighting scenarios with our lighting. And now, let's start off with the main topic of today, and Ivan is going to introduce that to you.
Thanks very much. So yeah, let's not lose time. We want to go into some examples, so let's dive deep into the UV and the sensitivity of imaging eye versus sensors. So as you know, we try to make the invisible visible, and with this, what still applies is it's imaging light, absorption and reflection, even in the peripheral areas, are not visible to the human eye. So the sensor has another sensitivity to wavelength, as you know, and of course, to those areas, we have additional sensitivity of the camera sensors coming from the UV area and coming from the shortwave infrared area. And I want to dive into the UV area first. So the UV in machine vision can be separated mainly into two areas. One area is the direct lighting, and the second area would be the fluorescence. Coming from the direct lighting, there are either it reflects the light or the light gets absorbed. If the UV lighting is absorbed by a surface, or maybe an object, a metal part with then the stamps on top can be reflected, or it can be absorbed by the stamps. Either or, the light is bright in the imaging camera, or it gets a dark spot. So having said that, in UV fluorescence applications, applying as much light as possible is part of the process, and it's very important since the emitted light has a longer wavelength and therefore has lower energy in the absorbed radiation. So this whole process is known as the Stokes shift. And right here we have an example for you. We photographed the bottom of a spray can, and with the visible illumination with white lightning, it is not possible to detect hidden codes or anything like that. But if you shine UV light onto the spray can bottom, then it is clear that you can detect some hidden codes on the bottom of the spray can. For this complicated exercise, of course, MBJ has got you covered. We have some standard lighting products newly in our product portfolio. It's the UV lighting from 365 nanometers to 395 nanometers. Of course, we have, over the years, made some custom projects ranging from about 280 nanometers to 405 nanometers. Diving deeper into UV, we want to improve the overall image quality. And how we can perform that is by narrowing down the range which the object emits. So if you shine the UV light onto your object surface and it emits bluish fluorescence, then it may not be enough because you have some side effects and you have too much other light coming from the fluorescence itself and maybe from the surroundings. So we want to narrow that down, and we want to use a filter for that, a narrow bandpass filter. Of course, it's a little bit of trying out the best bandpass filter possible and getting a clear image. Let me make that clear with an example. Right here, you see the detection of packaging damages. So when shining UV light onto this package, you see that there is a little defect right here, fluorescence in the greenish wavelength area. And of course, we can now try to detect this with a camera. But what happens is I've got a really strong reflectivity of the object surface. So the damage is not there anymore. It's not visible. And how we can help ourselves is we can add a narrow bandpass filter to our camera, in front of our camera. And we narrow that down. So we filter out everything which is not the fluorescence. And as you can see, it gets quite clear where the defects are. Another example would be the detection of foreign objects. To the human eye, maybe you have a look at the upper right corner. You see some pearls. They are colored in blue and white. Actually, those are medicine. And for the human eye, it is not possible to detect any foreign object. It looks like everything is all right. We shine UV light onto this medicine, and we take a picture with a monochromatic camera. And we still think it's pretty homogeneous. Adding the filter on top, we see that we can narrow it down. So there's only one ball, one foreign object in this medicine, which is fluorescence in the bluish area. And we can make out that pretty fast and detect a foreign object very exactly. Yes.
So I take over again, jumping to the other end of the spectrum, to the sphere spectrum. This is located in the infrared spectrum, so sphere is short for short-wave infrared. And I believe you've all heard of it, been in contact with short-wave infrared by now. It has been around for some years. It's defined as the area from the wavelengths of 1,000 nanometers to 2,500 nanometers. And what is fascinating about sphere lighting is that the wave or materials behave differently under these wavelengths than with what we are used to. So under sphere wavelengths, materials are penetrated by the light or do absorb the light in a different way than what we see with our own eyes. And I've brought an example here of absorption wavelengths. So these materials that you see up there will absorb the light and appear dark under a sphere camera lighted with sphere light instead of being white or transparent for water, for example. And for this absorption, we've brought an example. These coffee beans seem quite uniform here for our eyes. They seem quite homogeneous, and also inspected with visible lighting, they appear all the same. But when we illuminate them with sphere lighting and inspect them with a sphere camera, you see that some of the beans appear darker. And this is due to their water content. They have a higher water content, and therefore the light is absorbed at the wavelengths of 1,550 nanometers that we've tried out for this example. And this could be useful for quality inspection, for example. So water causes mold and can bring the quality of a whole harvest, of a whole batch down. And to prevent quality issues, you could sort out those water-infected coffee beans and prevent mold in a whole batch. And we've brought another example of the opposite effect that sphere wavelengths might have, where materials become transparent, are penetrated by these wavelengths. So we have a plastic container up here. It contains mint drops, and inspected with visible light, you kind of can see through, but not really. You have the print on the packaging, and everything disappears when illuminated with sphere light. So we know the effect that print disappears when illuminated with infrared light, but that the container becomes transparent is exclusive for sphere lighting, for the longer wavelengths of the sphere area. What is also interesting is how materials behave under different sphere wavelengths. So we have experienced that our customer are still oftentimes in an experimental phase with sphere lights and don't know exactly or can predict exactly how materials behave under different wavelengths. And it's worthwhile to try out different sphere wavelengths and see how the material reacts here. So you can see here a transition of transparency with different sphere wavelengths of the plastic container. One challenge with sphere light is that camera sensors oftentimes, or some of the camera sensors, are quite heat sensitive. This is why we laid special emphasis on developing a good thermal management of our lights. This is why our sphere lights are coming with such big heat sinks, so they prevent the camera sensor from heating up, improving the picture that you have as a result of your inspection. We offer 6 different wavelengths in our standard portfolio, ranging from 1,050 nanometers to 1,650 nanometers. We can do different wavelengths in between or going even above that range. And we offer different types and sizes of the sphere light to accommodate your inspection task. So with that, our time is unfortunately up. We hope this introduction into the sphere and ultraviolet lighting has sparked your interest. We are just over there for any questions you might have for your applications. Come to us and talk to us. We are the big orange wall right across the hall. And we thank you for your attention and looking forward to make the invisible visible with you. Thank you.
Thank you, Eva and Even from MBJ Imaging. We still have some time. Is there a question from the audience? One question, perfect.
Thank you. Do you have like light source or illumination that cover the full spectrum, like from the UV to like sphere?
You mean a combined device?
Yeah.
A broadband or hyperspectral?
Like the halogen lights, but halogen lights, they are quite easy to make the temperature higher. But I know that your light source, they don't have these effects. Thank you.
We focused on the peaks, so we don't have anything which is broadband, but we focused in the UV area and the visible area and the sphere area always on the peaks to get the maximum intensity. So it's always a trade-off, as you know, and we want to keep the temperature low, and we just focused on more intensity and more overdrive, which all our lights are capable of.